Hello everyone, welcome to the webinar. Thanks for joining us here today. Okay, so I will hand over to our presenter shortly. Today the webinar is entitled Introduction to High Performance Thermoplastics. We are joined today by Peter Cracknell, who is the founder of PSC Associates Limited. He set up this business in 2008, which serves the polymer industry within the UK and overseas. His work includes teaching plastics materials, plastic processing techniques, plastic product and mold tool design. He will be taking us through the webinar today. And if you have any questions as the webinar is progressing, there's a little box in your dashboard where you can type the questions and then we can ask them all at the end of the presentation. After this webinar has been delivered, the video of the webinar will be available on our website. So if you want to share it with any colleagues, you can do so and just sort of go to the homepage of the BPF website and go into events and then webinars. But I think that's it for me. So I will hand over to Peter, and if you have any questions, write them in the box and then I can ask Peter later.
Thank you very much. Right. This session, we're going to have a look at engineering, introduction to engineering and high performance polymers, thermoplastics in particular. So when we look at polymer families that we actually use, we have commodity plastics, which will be the polyolefins, styrenics, PVCs, acrylics. In terms of properties, they're much lower and more limiting in their use. And then we have an intermediate range of polymers, which we have our engineering plastics, the nylon, acetals, PETs, PBTs, polycarbonates. These kind of materials fall into that category. And typically we could classify those materials as being to withstand around 100 degrees C, the engineering application, without loss of properties for continuous use. If we move higher temperature, say up to 150 to 200, then that really limits nylon, it limits acetal, it can't take those higher temperatures as effectively. So we move into the high performance polymer territory, so we can classify really an HP thermoplastic as being able to withstand around 150 degrees or above continuous service temperature in use. And that really classifies polymers into three categories: the commodity plastics, the engineering polymers, and the high performance thermoplastics. Now, typically what I've done here, I've put a table together comparing engineering and high performance polymers, one or two commodity plastics on there, to show you the range of typical properties that we have when we classify polymer materials. So here I've got a number of polymers. I've got PEEK, polyarylamide, polyether ketone, PAA, polyarylamide. And I move down the list. We've got polyphenylene sulfide, PPA, nylon 6,6, PBT, polycarbonate. And then I've put in there glass reinforced PP, unreinforced and reinforced PP. And I typically put those in to show you how low for a commodity plastic the mechanical and thermal properties are compared to an engineering or a high performance polymer. The properties I've chosen here quite deliberately are density. As a comparison, you can see that the density changes quite markedly according to the polymer. Now in this case, I've deliberately chosen 30% glass filled grades of all the polymers, deliberately, because of the enhancement fiberglass gives to an engineering or any polymer really for an engineering application. As long as we can get the reinforcement to stick to the polymer and transmit from the polymer or its use to the material. So it relies on good adhesion with the fiberglass reinforcement to the material. Some polymers don't adhere so well, like polycarbonate. Others adhere very well, like nylon or polyester. So in this case, this matrix I've put together, a key property there is density, heat distortion temperature. That's the temperature. If we take a specimen, say I take this biro and I 3-point load it, I put it into an oil bath at 1.82 MPa load, and I apply that load, keep raising the temperature. At the temperature 1 millimeter deflection is reached, and we'll read that off as the heat distortion temperature. So in terms of applying these materials, the heat distortion temperature is of great importance to a designer selecting a material if they want thermal resistance. So the HDT is often overlooked by a number of people using polymers, particularly if they're not used to selecting plastics. The HDT is an unusual property that you won't find perhaps in metals or steels in particular, but is typical for polymers, and it is a limiting factor, the ability to withstand heat. And then we've got impact strength here, unnotched impact strength in this case. And you can see there's a big difference in impact strength over the polymer range. And then I've got stiffness and rigidity as also as mechanical properties. So that's not by any stretch of the imagination a concise overview of all the properties of polymers, but the key properties we look at from a design perspective. So I put the selection matrix together for the automotive industry initially, but have gone on to use it in the aerospace industry and the medical industries too. So putting all your polymers together, all your high performance and engineering polymers together on one data sheet is a very good way of looking at properties and making a choice and selection. I've left some properties off here, like cost per unit kilogram, whether it's flammability index, it's LOI, limiting oxygen index. So this really is just an opening property selection matrix, and it can be built on or modified to your company requirement. So that's just as an overview there of where the various materials come in basic mechanical properties. Now, points to note from the table that most of the polymers there, in fact all the polymers are represented of 30% GF, glass fiber reinforced. Most applications of these materials involved GF filled grades. Unfilled grades, although still useful, are less commonly used for engineering applications. If you want a surface finish, we often go for an unfilled grade, but at the cost of a lot of mechanical properties. When selecting a polymer for a high performance application, it's important to compile a material property requirement specification. Specific property requirements must be isolated and understood before you design the product. So as a consulting engineer, I'm often asked to look at an existing product, and quite often you'll see straight away that the polymer has been poorly selected. And they turn around and say, well, that's the way it's always been done. Might have been wrong in the first place, or simply that the polymers today weren't available a number of years ago. So what I've done here, I've put in a few examples of engineering products, quite common ones, that have been switched to a high performance polymer for production. And picking out the key points before you select the material is critical to the correct selection of an engineering or high performance polymer. So in the case of a diesel pressure pump housing, the key points for this product, because it would have been an aluminium die-cast alloy product, and the wish is to switch it to polymer, the key point there will be tensile strength. You're going to need good tensile strength on the top of a diesel engine, and heat resistance. You're going to need good heat resistance, so I'll put them in as key points. You're also going to need very good chemical resistance at elevated temperatures. So there are a number of key points I put straight in there. Are tensile strength at the operating temperature range, The operating temperature range itself from negative to positive, so it could go from -40 to +160 degrees C. So we're looking at our mechanical properties over that wide temperature range, and particularly chemical resistance. So we're looking to diesel fuels in this case, and flushing agents. I'd add that onto the list as well. I'd also add to that list UV stability, particularly on an automotive application, and impact strength. So there would be my key selection points for that application straight away. A pipe clamp fitting for a flange body. Again, this could be replacement of an existing aluminium product. And key points here are strength, toughness, working temperature range again. And if that's for a medical application, that's going to have to be sterilized. So it's going to see steam cleaning perhaps. So again, pick out your key points. Quite often, as a product has failed, you're asked to review it. I will just go through this little exercise, put down the key points, and just see which ones are missing. And quite often, the reason for the failure of the product in the fail comes out and hits you in the face. And quite often, it's quite basic. It's often silly things like lack of UV stability is often overlooked. So put your spec together. And then also, when we're considering high performance polymers, we must consider ease of processing or the processing of the material at the selection stage. So here I've listed 5 high performance thermoplastics. We've got polyarylamide, polyarylimide, polyether ether ketone, liquid crystal polymer, and polyphenylene sulfide, PPS. Ease of flow, I've categorized these again, just an extension of what we were looking back on the previous page. So ease of flow, low when it's unfilled, it's easy flowing, low viscosity, easy flowing when it's unfilled. Put the filler in and the polymer becomes a medium viscosity with fiber reinforcement in it. It exhibits a narrow processing window. So you're going to have a hot mold and a very narrow heat window to process the polymer. If you do too cold on mold temperature or too cold on melting point, or the melt temperature is too low, then the viscosity can increase quite rapidly, and hitting the correct processing window is essential with these materials, particularly when filling the cavity. All of these high performance polymers lose heat rapidly as soon as they enter the cavity. So that really does narrow the processing window right down. You're going to have a very hot mold straight away with these materials. And often the biggest mistake I see with processing is some of these narrowed the processing window too low by using too cool a mold. And that restricts the flow time in the mold. And that's a very common mistake people make with these high temperature, high performance polymers. They haven't got the mold hot enough for a narrow processing polymer. So if you're even 10 degrees below the recommended mold temperature, that's often too much for a high performance polymer, and you will have trouble filling the cavity. So a narrow processing window is typical of these high performance polymers. Now, what is also different to a commodity plastic is the projected area force requirement. Now, these are actually measured values I've taken off an injection molding machine. And you can see for PAA unfilled, it's around 3 tons per square inch, or 45 MPa for every unit projected area. If we put fiberglass in, say 30%, then that easily rises to 4 tons per square inch, or 60 MPa. So you have to be aware that the change in viscosity caused by the filler increases the clamp force requirement and injection pressure requirement on the molding machine. Now, some high performance polymers are even more sensitive than that. You go down to PAI, this is a very high viscosity material, trade name is Torlon. Very narrow processing window. If the mold is slightly cooler than it should be, the polymer freezes almost instantly on contact. So you're going to need 7 tons per square inch of projected area in a reasonably filled grade of polymer, perhaps 20%, move to a 30 or 40%, and that easily jumps to 10 tons per square inch. So there, a change in grade will really increase the clamp force requirement for these materials. A lot of the technical data is often too general and will state a generally low value for clamp force, where in effect you actually need a much higher value. With PEEK can be quite an interesting polymer because it can change according to the wall thickness that you're actually dealing with. So again, a very narrow processing window. With PEEK, you'll find it is actually starting to solidify at around 350, 345 to 350. At 375 is really its optimum melt temperature for unfilled PEEK. But you might need to go even hotter once you put more reinforcement in, carbon fiber or glass fiber reinforcement, for instance. So the actual processing window is very narrow. If you drop the barrel temperature 10 degrees below the recommended melt temperature, that increases the screw torque drastically on the molding machine. In fact, if you go too low, creep too far towards 350, you're in danger of snapping the screw with certain grades of PEEK, depending on the fiber reinforcement used. So a medium filled grade of PEEK, you're looking at around 3 tons per square inch, 45 MPa clamp force requirement, and that jumps quite considerably with a highly filled grade to around 4.5 tons per square inch. That's quite a big difference. Liquid crystal polymer, again an easy flowing polymer, but still exhibits a narrow processing window. This is a polymer where the flow viscosity changes quite drastically according to the melt temperature. So 20 degrees drop in melt temperature could easily double the melt flow viscosity with LCP, depending on the grade you're dealing with. So unfilled grades, 2 TSI is fine. With more filler, glass filler in it, you have to jump to 2.5 TSI. Now that's relatively straightforward, but the problem with LCP is filling speed. You have to get the filling speed up because it has a very low specific heat content. It loses heat rapidly as it's filling the tool. So you can't hang around with any of these materials filling the mold. PPS, this is really 2 polymers within one, and an unfilled grade fills very easily at around 2 tons per square inch. But a medium mineral filled grade, a medium viscosity grade, still exhibits a narrow processing window, but you're going to have a much higher mold temperature with a filled grade. It'll go from 140 or 120 to more like 160 or 180. The mineral filler also increases the incompressibility of the material, hence the higher clamp force requirement, and your filling speed will have to increase too to avoid premature freeze-off. Looking at the actual mold temperatures, these are mold temperatures taken off actual molding machines, so they will vary according to the technical data from a number of the material suppliers. So you see the PAA there, typical melt temperature 275, and here's the temperature profile. The mold for an unfilled grade will be 90 and 140 for a filled grade. So a 50% GF grade, I'd be looking at a mold temperature nearer to 140. Lower barrel temperatures at the rear, higher in the middle, tapering down to the front. Nozzle temperatures for an HB polymer are very important, that you maintain the nozzle temperature, depending on the grade. So the higher temperature here will be for the higher filled grades, the lower temperature for the unfilled grade. Again, PEEK, you can see there's a big difference there in mold temperatures for an unfilled grade as opposed to a filled grade. Big difference from 160 to 210. You might get away with an oil heating at 160, but at 210 is really electrical heating. I'd go for electrical heating, anything above really 180. Okay, and again, the difference in barrel 340 to 360, you see there's quite a big difference up to 390 there for a filled grade. LCP again, big difference here, particularly in melt temperature, you can see between an unfilled and a filled grade, and also in mold temperature. Again, it doesn't look much, but to LCP, that's a massive difference in temperature. The same as peak. Peak is tremendously temperature sensitive. It will also stop the polymer from crystallizing if it's too cold, if the mold is too cold. So the mold temperature is essential for these materials because we have to hover the material around the crystallization temperature for longer. The molecules in these materials are stiffer, so they take a little more time to order themselves and to crystallize. PAA and peak in particular can take a little more time to crystallize than normal engineering plastics. You'll get a change in color when you get the correct degree of crystallinity, particularly in peak. Again, PPS, big difference between an unfilled grade and a filled grade. That 20 degrees doesn't look much, but it's a big difference to the polymer in terms of filling efficiency. So as I mentioned there previously, we've got to hover around the crystallization temperature for this material. So as we come down during cooling, we like to spend more time at the crystallization temperature with these engineering and high performance polymers. So the stiffer the molecule becomes, the more time it's going to need at the crystallization temperature to crystallize. And certainly with peak, you're going to want to maximize the percentage crystallinity. The maximum you're going to get is around 35% anyway, but it does make a huge difference to the strength of peak in particular, the more crystalline the polymer becomes. So hovering around TX or the crystal TC or TX is often in many texts the reference for the crystallization temperature is very important, and also for polyamides. It's important that we hover around the crystallization temperature if we can for a polyamide for as long as possible. More aromatic the polyamide, the more the benzene rings in the backbone, the stiffer the molecule becomes, and the more difficulty the material has with regard to crystallization. But you're going to need to promote maximum crystallization to get your best mechanical properties, particularly impact strength and tensile strength. Now, another feature of these materials, all of these high performance materials, are their shrinkage. They are highly anisotropic, even without a filler in them, because the stiff molecules are much stiffer than, say, the commodity plastic or an engineering polymer, and they'll orientate quite heavily in the direction of flow. This flow orientation means the stress pattern in the polymer tends to follow the flow orientation effect. So particularly with peak and PPS, well, particularly peak, you're going to like bigger gates and PAI, much bigger gates, to reduce the stress flow orientation effect. So wider gates for peak assist in the mold filling and also give you a more homogeneous range of mechanical properties. Peak in particular will highly orientate if constricted badly in a flow stream, and particularly if you put fiberglass or carbon fiber fibers in any of these polymers, would cause very high degree of gate stress orientation. Even with peak, you can end up with brittle gate syndrome if you've over-orientated or packed too much filler into the material and it's heavily orientated and focused on the gate. So you won't obtain the high impact strength of that polymer at a highly orientated gate. You could risk quite low impact strength at the gate due to high orientation. So lowering the orientation by using a wider gate assists the reducing the level of anisotropy in the polymer. Okay, now, because of this high level of orientation, partly due to the filler in the material, the glass fiber, and the unfilled grade, you're going to see there's a big difference in shrinkage. So the unfilled grade there of PAA, you can see shrinks in the A direction, in the direction of flow, about 0.5% for a 1 mil wall, and about 0.6 of 1% at 90 degrees to the flow direction. However, if we introduce the fiber to the material, it becomes a different animal. In the direction of flow, the shrinkage drops to about 0.2% in the A direction and direction of flow. At 90 degrees, it's still the same at about 0.6. So you've got treble the shrinkage in one direction, transverse to the flow, as opposed to the direction of flow once you put the reinforcing fiber in. So be very wary of particularly cavity sticking issues when changing flow direction. Peak can be highly sensitive once you put the fiber in. Let's have a look at peak here. So we've got, in this case, a 200 to 1 filling ratio. So for a 1 mil wall, it's going to flow 200 millimeter for a 1 mil wall. Once you put the fiberglass in, or the carbon fiber, that drops to 80 to 1. So an unfilled grade of peak there can easily have a very good flow ratio of 200 to 1, but that drops to 80 to 1 as soon as your glass or carbon fiber reinforce. Also, the material changes its shrinkage characteristics drastically. Unfilled, it shrinks about 1% in the flow direction. Transverse to the flow, about 1.6%. Now that doesn't sound good, but actually that's a desirable characteristic because it makes cavity release very easy. Now, cavity release is a key issue with a lot of these high performance polymers. You can gag the cavity very easily by shutting down the shrinkage. So with peak, as soon as we put the carbon fiber in, or the glass fiber, it suddenly changes. This catches a lot of people out. In the direction of flow, the shrinkage there has dropped to 0.05%. That's not a typo, it's actually a measured value. And it's increased to 1.4% across the flow. So across the flow direction, it is similar to the unfilled polymer. But what catches people out, in the direction of flow, all of the fiber reinforcements are queued up and orientated like logs flowing down a river, and the logs are back to back, end to end. And that's taken up the free volume in the polymer. So now we're fiber ending the filler one on top of the other as the polymer cools. And that, if you overpack peak, you can actually get negative shrinkage in the direction of flow. It'll actually grow slightly in direction of flow, and then you just hope that your molding machine is powerful enough to open the mold, because it's going to stick hard in the cavity or hard onto the core. Liquid crystal polymer, you can see, does exhibit negative shrinkage. Fiber loaded, you can see it's 0 in the A direction and only 0.4 across the flow. So mold sticking is a big problem with LCP. Its flow ratio is outstandingly good at around 350 to 1, unloaded. And quite often you really don't need the fiberglass in LCP because you're not getting a huge change in the mechanical properties. This is a polymer that self-reinforces and is often better to mold it without fiberglass in it. PPS is more user-friendly than the previous materials when it comes to shrinkage. For only a 10% filled grade, you've got a good flow ratio there, 150 to 1. Put the filler in it. Now, PPS can have very high percentage levels of filler, and quite often it's a package of mineral fillers and fiberglass. So we mix mineral filler in with fiberglass as a filler package with PPS. That's not uncommon. And as a result of having the mineral filler in there, you can see that there's quite a big difference here in the shrinkage ratio. So at 60% glass fiber loaded PPS, which is not uncommon, the A shrinkage in the direction of flow drops to 0.1 and 0.5 in the B direction. So it can stick quite hard in the direction it's flowing. So when you're designing with these high performance polymers, you have to put adequate draft angles, particularly in the flow direction and particularly in the cavity of the flow direction that you're filling. So designers soon get used to that and avoid bunching the reinforcement at the gate. If you bunch the reinforcement at the gate, you will focalize the stress to the gate, and even these really strong polymers will suffer gate embrittlement as a function of focalizing all of the reinforcement pointing towards the gate. It'll be very strong in tension, but very weak in impact, particularly at the gate. Get away from the gate and the polymer is back to its normal self. Good impact strength and everything, but particularly vulnerable around the gate. I copied this, borrowed this off Victrex a number of years ago, and it visually shows the melt viscosity ranges for a range of high performance polymers. So you've got a polyamide imide up here, and notice on the viscosity sides to this viscosity curve, you've got poise on one side, 10 to the power of 4, 10 to the power of 3 poise, and viscosity in newtons seconds to the -2 there, meters squared, 10 to the 2 and 10 to the 3 in poise, in viscosity, and 10 to the 4 in poise. So there's a correlation there, 10 to the 3 in normal viscosity and 10 to the 4 in poise. Now, anything above 10 to the 3 is starting to be a problem in terms of viscosity, and I would classify that as a higher viscosity polymer. A medium to low viscosity polymer would be below 10 to the 3. Okay, now viscosity flow curves are very useful for a setter on a molding machine, because the center of the curve, if we take that down to the bottom of the chart, so if I pick up 450G peak and I take the center of that curve, that would give me the target melting point on the molding machine or extruder. So always work to the center of a flow curve if you can with a high performance polymer. Now notice that the curve stops at around 360. So really the viscosity is starting to increase. Certainly at 340, the viscosity will be very high for this polymer. It'll be well upstairs, and it won't be melt processable. You might be able to compression mold it, but certainly not injection. You risk snapping the screw. So this exhibits here for peak a very narrow processing window indeed, where you really want to target the center of each flow curve. Nylon 6,6 again, you can see unfilled nylon 6,6, the best flow really with control for the setter is bang in the middle of the curve. By dropping the temperature by a good 30 degrees, we'll drop that to around 270 degrees, and the viscosity has increased quite markedly, and that gives you a lot more control over the polymer during processing. Whereas if we operate too far down the end of the curve with nylon, it's too liquid and too close to degradation. And the forerunner of degradation is a drop off in viscosity. The viscosity decreases as the polymer starts to degrade, as the molecular weight starts to shorten, so the polymer flows easier. So I see a lot of setters running nylon often too hot. And again, with polypropylene, we really want to aim for the middle of the melt temperature range if we can, which comes out at around 240 each time, giving the setter there plenty of latitude in heat as a setting control and reduction in heat as a viscosity control. So with these high performance polymers, notice the shortness of the curve and how high the curve is up the viscosity range. And that's fairly typical for a lot of these high performance polymers. That's a typical characteristic. So now, grade for grade, these curves could change quite markedly for some high performance polymers. Their ease of flow changes according to the filler that's been added to the material. So there's quite a marked difference from grade to grade. Freeze flow characteristics of a high performance polymer. Polymers often flow in a pseudoplastic form. The Americans call that plug flow. So it takes up a plug shape. So when the polymer flows down a channel, say in a mold, it creates a skin on the surface, and then the polymer flows inside the skin. Where the skin is in contact with the lower polymer flowing layers, you get a lot of internal shear. It's like rubbing your hands together. So the hand facing the screen with a wedding ring on it is the skin, and my right hand coming towards you is the polymer flowing. So the faster I go, rub the skin, the harder and the higher the temperature becomes. And it's this in keeping this temperature nice and high with a high performance or an engineering polymer, which is fundamental. If we drop the shear too low, then we're losing the melt temperature quite rapidly. And with a very narrow processing window, that's bad news with a high performance polymer. So on first stage injection, up to 98% cavity fill, we must maintain quite a fast filling speed to maintain high shear and the melt temperature through the filling profile. Now we've got a problem. These polymers all exhibit high heat distortion temperatures, and they solidify at a very high temperature. They wouldn't be a high performance polymer if they didn't. Now the problem we've got a static slug of material at the front of the melt flow that develops a cold nose. With a high performance polymer, a lot of these polymers like PEEK exhibit quite low specific heat contents, so they lose their heat quite rapidly. And as a result of that, this cold nose here at the front of the melt flow can actually solidify quite quickly. It won't fully solidify, it will gel up and become quite rubbery, but quite incompressible. And that will be forced all the way through the molding. And particularly with PEEK moldings, you'll often find great difficulty in knitting weld lines the further you are away from the gate. And quite often that is due to melt temperature loss during the first stage injection pressure. So you need to get to about 98% cavity shot weight on the first stage as fast as possible to maintain the melt temperature, because PEEK loses heat rapidly as you're filling the tool. You can't get the weld lines because the polymer, you can't knit the weld lines up on the extremities with PEEK and other high performance polymers because you've pre-gelled the polymer. It's not actually liquid by the time it reaches the extremity of that mold. So we need a cold flow trap feature, or I like to run a high performance polymer through an open nozzle, a direct feed onto the component. So no sprue or feed system, direct feed, and by direct feeding overcomes the cold nose slugging issue. Direct feed or a hot tip sprue bush, for instance, straight into the molding. And this overcomes the cold slugging issue. So cold slugging is a major issue with a lot of high performance polymers, that we're losing too much heat during the mold fill phase. The more filler you put in, the quicker you lose the heat. So you need a much hotter mold and a hotter melt temperature. The optimum flow shape for a polymer flow for a high performance polymer is round. So the frozen skin will absorb a lot of the pressure transmission area, and this becomes dead material. So the frozen skin doesn't contribute to the cavity packing pressure at all. It detracts from it. If I put in a square runner, then there'll be a lot of dead frozen polymer in the four corners, and that detracts from the packing pressure straight away. And it's also throwing polymer away. because that's ineffectual. It's one reason we like to direct feed with an HP polymer. Okay, I'm going to scroll on. I'm running out of time rapidly here. Gate geometry. The high viscosity and short processing window exhibited by many of these high performance polymers mean attention has to be paid to gating. Now, as a consulting engineer, I see some of the biggest problems with HP polymers and also nylon and acetal is with gate selection. The high flow viscosity and short processing window means that we have to pay particular attention to the following problems. Fiber bunching in small restricted gates. It doesn't have to be fiber, it could be carbon platelets. It could be actual molecules of the polymer too. With these highly ordered molecules, you can get bunching at the gates of the actual molecules as much as the fibers. The fibers just make it worse. Cold slugging, it give you partial gate restrictions, loss of cavity pressure, particularly with submarine gates or pin gates. Fiber breakage through gate restriction, particularly with very brittle carbon fibers, can be a major issue. Breaking the fibers, you have to have a critical fiber length with any engineering polymer or high performance polymer, at least 100:1. So if I divide the diameter of the fiber into the fiber length, it has to be at least 100:1 or above to give you a decent critical fiber length or strength ratio. If the fibers are shortened by fiber degradation during filling, you're reducing the overall performance mechanically of the final composite polymer, the injection molded polymer. Quite often I'll do a soot test where I'll actually burn the polymer off in an oven and examine and filter the fibers and then work out the critical fiber lengths. And quite often you'll find you've halved it by going through a restricted gate. Okay, melt flow stalling. A big no-no with these high performance polymers is stalling the melt flow. So as it travels round the feature, you don't want it to stop and then carry on filling. It must fill the cavity in a button format uniformly all the way through. So jetting is a big no-no with a high performance polymer. As soon as the polymer jets, it chills, cold noses, and you've got no chance of welding it up. So if we do have any melt flow stalling in the cavity filling profile, you can end up with cold flow voids in the molding. And the first giveaway will be a change in shot weight. You'll find that shot weight will go down and the degree of inaccuracy will start to kick in. Impact strength will reduce and polymer shrinkage will start to become a little more wild. It will start to drift a little with the material. Inconsistent shot weights and underpacking poor quality components are a feature of a poor or a semi-stalled melt filling profile. Okay, now what I've done here, I've put in some QA shot weight analysis of a PPS job. And this was an automotive supply job. Can't mention names because of NDAs, but it was a PPS job. 40% glass-filled PPS. I can tell you it was Fortron. Batch 1, somebody had used a 1mm diameter submarine gate and a mold temperature of 130 degrees C. And batch 1, the shot weight there varied from 20.55 grams to 20.25 grams for 16 consecutive shots. The range over 16 shots was 0.3 of a gram. This product had to seal and on overmolded pins, and we found they were leaking. So the shot weight was too light and it was too variable. So the scrap rate was very high. By opening up the gate and increasing the mold temperature from 130 to 160, batch 2, the gave a shot weight there variance of 20.55 to 20.59. And straight away, that's right bang in the ballpark of where you want to be. You want a very narrow shot weight variance with any polymer really, but particularly with a high performance polymer, and a very narrow range. So the shot weight range in this case was 0.04 grams. And that really is the kind of target you want to be with PEEK, pipe PAA, all the other high performance polymers. You need to be in that ballpark. And quite often, I get a little bit concerned when I go into a mold shop and they're molding a high performance polymer. They've got a lot of problems and they don't have a set of precision scales. So we need 1,000 resolution scales really to pick out the narrowing of the processing window or the shot weight variance. So the use of small width and shallow restrictive gates should be avoided when using fiber loaded high performance polymers. Any loss of temperature or blockage induced pressure drop in a melt flow can cause the polymer to stall. It's only got to stall for a fraction of a second. If the flow front hits a cold spot in the cavity or the gate is partially blocked by bunching, by fiber bunching, once stalled, the melt front cannot change direction. It will change direction once it stalls, and it can't backfill the feature afterwards because it's already frozen. The damage is done. The polymer would have frozen and cold flow trap void created as a result. The polymer flow processing window is often too small with these materials, and many component defects can be traced back to the poor filling phase with these materials. So you want a very smooth filling phase with no stalling at all as it fills the cavity, and no gate bunching either. Gate geometry, standard gate geometry here, LT and W. The length of gate land influences the pressure drop in a gate. The width of gate influences the burst pattern. The width of gate influences burst pattern. And the depth of gate T, the volumetric throughput through the gate in meters cubed per second. So all three come heavily into play here. But in particular with a high performance polymer, the width of gate, we need to get this broad button shaped filling profile. We often call that the fountain effect, but a nice button profile as opposed to a narrow profile or a jetting or worming profile. I always take the filling time off in seconds on the first stage back to 0.1 to see what the exit profile of the gate is, particularly on an engineering polymer or a high performance polymer. If I don't get this button forming on exiting the gate, I know I'm in big trouble, particularly with PEEK and particularly with PPS. Okay. So again, fan gate gives you a good wide button profile. We look for this button profile, and then once it's established, the polymer flow front follows that button profile quite effectively. Submarine gate there, restrictive, highly restrictive. Okay, perhaps you get away with an unfilled grade of PEEK, but certainly not a filled grade of PEEK, which can be disconcerting because people like to use the same gates for all the different grades, but you can't. You're going to have to change the way you think. Product design considerations. We select high performance polymers, although they're costly. Main reason is cost reduction. So in terms of replacing a more expensive machined metal product, the example there could be pump parts made of stainless steel. If you injection mold them in PEEK, they're much, much cheaper once the tooling is established. I can remember one job I worked on as a consulting engineer. We got the payback from the cost of the tool within the first 20 minutes of production, because the CNC costs of routing out stainless steel components was prohibitively high. So we recovered the PEEK tool cost rapidly on that job within the first 20 minutes of production. Is not uncommon. Reduction in assembly and fitting costs. In this case, switching to glass-filled PP over molded components really eliminated copper radiators and enabled us to use aluminium and overmold the ends. Another one here I've put in there, examples of there are specific properties of high-performance polymers. And here the use of Kevlar for body armor, PTFE for non-stick low friction applications, FEP for medical applications, polycarbonate for headlamp lenses, LCP in microwave ovens. LCP there is transparent to microwaves, it doesn't heat up. And with a lot of these high performance polymers, they have peculiar mechanical properties or physical properties. Once you get to know them, you can use them to their strengths. PAA for marine construction, nails and screw fittings. Obviously, its big use there is anti-corrosion. Okay, I'm going to skip through this, the do's and don'ts. No, it's important, I'm going to cover it. Design components, design components which exhibit natural balance in terms of filling profile. You've got to flow to the same direction in all directions in a high performance molding to get good uniformity of fill. Don't put shut-off detail at the last place to fill, because you're never going to knit that weld line in a high performance polymer. It's going to be very difficult because it will have lost too much heat. Be very aware of the shrinkage and the cooling requirement of these polymers. Be very aware of what you're doing in terms of shrinkage and the product design. The ejection force requirement, if the shrinkage is very high and it sticks to the core, can often be beyond the molding machine. So quite often with a high performance polymer, if it's stuck to the cavity or the core, you find that the molding machine isn't powerful enough to eject it, or in a very bad case, even open the cavity interface. Stay within the natural flow ratio for the polymer being processed. Don't go beyond it. If you go beyond the flow ratio, then the setter's going to have to blow the mold apart to fill it. Okay. Avoid sudden changes in wall section. Avoid the creation of melt accumulation or hotspots in the cavity or the mold tool. Avoid features which could stall a melt front. In other words, a shut-off detail a long way from the gate. So the polymer hits it, thrown sideways, stalls. Do not overlook the draft requirement for the polymer being processed. That's critical for a high-performance polymer. Do not design a component feature which is impossible to heat or cool. Heating being the key one here with these high-performance polymers. So make sure you've got good heater coverage. I'll often design a cavity or a component I know fits a standard heater profile or shape. And that is really the key to processing a lot of these high-performance polymers. Now what I've done here, I'm running out of time desperately fast here. So I've put in some technical data here on PPS, a few trade names, well-known trade names, and a chemical repeat structure. I've also put in typical reasons to select the material. In the case of PPS, good long-term thermal stability. It's UL rated for 200 degrees C for continuous use. Good creep resistance. Enables precision molding to tight tolerances with good shot repeatability. Excellent chemical resistance. This is often overlooked with these materials. And natural non-flammability and good electrical insulating properties. It's one of the few polymers that has a naturally very high limiting oxygen index. That's often overlooked when people selecting PPS. Excellent property profile at 30% glass filled. Add to that its outstanding chemical resistance. It's a pretty good polymer and it's relatively low price. Typical design data. we can actually, because its flow path ratio is around 150:1, we can use it in a nylon 6/6 mold, often without modification. So we can go straight in to a mold that we were previously running on nylon 6/6 without modification. So quite often I'll trial a job in glass-filled nylon and run off glass-filled PPS in the same mold, just upping the mold temperature at the same time. Thinner wall sections, you're going to need a lot more clamp force with PPS. It almost doubles. So if you drop down below 0.5 mil, you often have to double the injection pressure and double the clamp force to resist it. Okay, I'm going to jump through to peak, just spend 5 minutes at peak. So there's lots of extra notes here to go through, which you can read at your leisure. Now, peak here, if I substitute the oxygen atoms in peak for an S, the sulfur atoms that you have in PPS, it becomes a polysulfone. So the nearest relation to peak chemically is polysulfone. And again, if I substitute the sulfur atoms in polysulfone with an oxygen atom, it becomes a ketone. Peak is an outstandingly stable, thermally stable chemical structure. It is semi-crystalline, typically up to around 30 to 35%. It needs a bit of time to get 30%, so you need to hover it around its crystallization temperature for a fair bit of time. It likes at least 8 to 9 to 10 seconds at its crystallization temperature to get the crystallinity out of the material. In terms of property profile, it doesn't really have a weakness. Good long-term thermal stability, UL rated to 240. Material is tough, abrasion resistance, exhibits excellent fatigue resistance, brilliant bearing properties over a wide temperature range, good chemical resistance, including hydrolysis, exceptional radiation resistance, so it's brilliant to use in power stations, nuclear power stations. A lot of medical applications there have radiation, so it's a good material for that. Naturally V0 rated, so an excellent material for aerospace applications. I'd like to show you components, but I can't because of NDAs. And outstandingly good electrical properties. Again, this polymer is overlooked often for the electrical properties. It's a very good electrical property material. So again, an excellent property profile. Can be a little bit on the pricey side, but you do get what you pay for. And there I put in some typical design data, flow path ratios, how to design the components, considerations you put in. Again, the injection force requirement will have to increase if you drop down to 1 millimeter. So we're going to jump up to 4.5 tons per square inch quite easily by changing from a 3 mil wall to a 1 mil wall. And that's quite an important feature with a lot of these HP polymers. And again, screw and barrel requirements, heating requirements, I've covered here in the data. And again, designing, avoid weak weld lines. Don't design shut-off detail a long way from the gate because you simply won't be able to pack it. Okay, right, I'm going to wind this session up here. So I've already overstayed my welcome. We're an hour out now. So any questions? Does anyone have any questions I would like to ask?
Mute. I should be off mute now. Can you hear me?
Yeah, I can hear you.
Excellent. Okay, so for everyone listening in, the question box is in your little dashboard. There's like an orange. There should be like an orange.
Is it chat?
Chat is yes, they can write questions in chat as well if they wish.
Right, there you go. I've opened it. I've opened the chat box. So if there's any questions, feel free to type one up. Now, with these polymers, the rules are actually quite easy to follow. You've got to keep the heat in the molten polymer as it flows through the mold. If you allow the melt temperature as the mold is filling to drop, then the polymers start to misbehave. They start to chill off, and you won't get the performance out of the material. They also like to hover around the crystallization temperature to give you maximum crystallinity available in the polymer for the best mechanical properties, without any doubt. So quite often, one of the biggest crimes with a high performance polymer is to have the mold too cold, far too cold. And quite often, oil heating simply isn't enough. You have to use electrical heaters 9 times out of 10, particularly with PEEK and PAI, polyarylamide. Okay, I don't seem to see any questions coming up there. Is it possible for the attendees to download these notes afterwards?
Yes, it will be. Yeah. So
that's great. Yeah.
What we'll do is we'll upload this video, and then underneath the video we'll put the notes, which is basically this PDF that you've been going through, and then we can include this in our newsletter so people can download the notes as well from there. The place they need to go on the website is you need to navigate to the events. Go to bpf.co.uk, navigate to the events, go to webinars, and then there's a button you can click that takes you to all the old webinars, and that's where you can download everything. That's where you'll be able to access these.
Good. All right. If there's no more questions, then we'll call it a day. I don't think there is any. Okay then.
No, not seeing any popping up. Thank you very much, Peter, for that. That was very informative. And yes, thanks everyone for joining us, and we'll see you again soon. We've got a big packed roster of webinars coming up over the next couple of days and weeks. We've got an event tomorrow on PVC innovation and the drive for circularity. We've got a Brexit update for all those interested in policy matters.
Yeah.
That's happening on Friday, I believe, November the 20th. So you can sign up to that if you're interested in learning about that. That's happening straight after some EU summit, I think. So, and it's being presented by someone from Bays. So it might be interesting to.
That could be interesting, that one actually. Yeah. Okay, right. Thank you.
Cool. Right, thanks everyone. Thank you, Peter.
Okay, then. Bye.
See you later. Bye-bye.
Bye.